Did you see the recording button? There is a recording or recording somewhere. Okay, great. So it's recording. So I'd like to welcome everybody to our first webinar in 2025. This year focus will be on artificial intelligence application on petrophysical domain. We start this year with Dr. Steve Cuddy. He's ex-Baker Hughes for about 22 years. He can, for sure, he can introduce himself better than me. I will just make a small presentation before we start. And Dr. Mohammed, if you want.
Yes, Mr. Mazen.
Yes.
Hello, everyone. Today is the 20th of January, 2025. On behalf of the SPWLA Iraq chapter, we are thrilled to welcome you and have you join us today. My name is Muhammad Jawad Zainul Abedin, and I am the Vice President of Technology at the SPWLA Iraq chapter, as well as a senior faculty member in the Department of Petroleum Engineering at the College of University of Kirkuk. The first webinar in 2025, the benefits and dangers of using AI in petrophysics, will be presented by our speaker, Dr. Steve Cuddy. Welcome again, Dr. Steve Cuddy. And dear attendees, please note that during the presentation, we will share a link in the chat box to join the SPWLA Iraq chapter on LinkedIn. Thank you, and Mr. Mazen, the floor is yours.
Who we expect to speak? Is it Mazan or is it me now?
I think Mr. Mazen can speak. Mr. Mazen, can you hear me?
I was muted. Okay, I was muted. Okay, so thank you, Dr. Mohammed. You can see my screen that I just shared.
Yes, sure, Mr. Mazen.
Oh, okay. So I'd like to welcome our attendees for this first webinar. Just for the record, my name is Mazen Hilali. I'm senior petrophysicist with Look Oil International, working in their South Iraq project in Basra, West Ghouta 2. This first webinar will be on the benefit and danger of using AI in petrophysics, presented by Dr. Steve Cuddy. We plan this year to do 11 webinar. At least we have confirmed the first 6 webinar till June. The other webinar will be confirmed subsequently. Hopefully we are targeting at least to make 10 to 11 webinar this year. Next webinar will be with Mr. Craig Phillips with Python application in Carbonate Petrophysics. We target to be in February. Afterward, we have with Spotify, Microsoft, and BP, and Open Petro AI. And the other presentation will be confirmed later. Okay, one by one. As usually here for the attendees that will attend 6 webinars, we'll give them a special super learner special certificate. We didn't award the 2024 till now, if somebody is asking, because we're still getting a request and we audit these requests. Hopefully today or tomorrow, okay, we'll start sending the certificate. Will be appreciated your joining to Iraq chapter and to the SPWLA organization. We'll appreciate to keep the question and answer at the end of lecture, and you can write it in the chat box. Thank you so much, and the mic is yours, Dr. Steve.
Right. Can you see my presentation there? Can you see it?
Yes, yes,
That's
yes.
the
But
first
not on
slide.
the, yeah, but not on the, now it's in the presentation mode. Yes.
Right. Okay. Well, thank you for coming along to this presentation this afternoon and this evening. And this is what it's all about. It's based on a paper, as you can see on the top right-hand side, which I'll give you a link later. So this is an outline of my presentation. I'll give you a very simple definition of what is artificial intelligence, AI, and I'm going to go through 5 real case studies or real data where the AI was used in anger. I'll also tell you about the difference between narrow, general, and true AI for information. And then I will finish by talking about the dangers of AI. And when I say dangers, I'm not saying making a poor petrophysical interpretation. I'm speaking about an end of civilization event, really. So, what is artificial intelligence? The godfather of computers, Alan Turing, he said it was getting computers to imitate human intelligence. Such that if you look through your window and you saw it was raining, you probably think, well, I need to take an umbrella. That is natural intelligence. If the computer knows what the weather is like and it recommends you carry an umbrella, that is what we call artificial intelligence. Now, AI, I'll just put onto laser pointer. It's a kind of data analysis. It learns from data, it identifies patterns and makes predictions with a minimum of human intervention. And I'm going to go through 3 generations of AI. Very briefly, the first generation of AI, this was available in the 1970s when laptop computers became available, and it's what you call an expert or rule-based system. So you could do simple petrophysics. Excuse me. So it would say it was simple rules. If the gamma ray was over 50 API and the porosity is less than 2 porosity units, it is most likely to be a shale. That was the rule-based systems, and that is not considered nowadays to be artificial intelligence. Using the same kind of system, back in the 20th century, IBM developed a computer program called Deep Blue, which actually beat the grandmaster at the time, Garry Kasparov. That was the first generation, a rule-based system. Now we're into the second generation of AI, which I would call machine learning. And I'm going to show you 5 examples of that. Using the second generation of AI, Google's AlphaZero self-taught itself chess without any rules, and it easily beat the first generation AI. And out of interest, I'm going to tell you about the future, the third generation of AI, which is general intelligence. Excuse me. So first of all, you have to tell the AI what you want. This is its goal or its fitness function. And I will explain later why it is called a fitness function. The second thing you give it is the data, and that is all it needs. There's minimal human interaction. The AI doesn't require prior knowledge of the petrophysical response equations. There are no parameters to pick or cross plots to make. You give the AI access to all the data. You're familiar with the electrical logs, like the gamma ray, the density, caliper, etc. You also give it the core data, core porosities, water saturations, as I'll show you. You all give it the depth, measure depth, and TVD sub C. These are probably the most important parameters. You give it the gas chromatography data, which is essentially a free measurement because it's run in every well for safety reasons, but it contains valuable information about the well. You can give it the drilling data, rate of penetration, etc. And as I'll show you, you can also give it advanced measurements like nuclear magnetic resonance. Now, do not worry if these data contain garbage. As I'll explain later, these are automatically ignored. Now, the data arrives as an n-dimensional array. One of those dimensions is, say, depth, or it could be time. That is the one dimension. And a one-dimensional plot of, say, density is shown here in the top left. So it's like a frequency plot or an histogram. So you've got density and its occurrence. That's one dimension. Two-dimensional data representation is, say, a cross plot, as you're familiar with density porosity against neutron porosity. And this is a two-dimensional plot. Then working upwards, three-dimensional plot is difficult to show, but if you color the z-axis, say with the gamma ray, you've got a three-dimensional plot. And this continues upwards to n dimensions, where n is the number of inputs, which is unlimited. And it's all plotted in your relational database, as I say, against depth or time. This is what you give the AI. So you only give it two things, the data and then the problem you want to solve. So you define the problem, it's called the fitness function. The computer program, the AI, guesses the answer and through successive iterations or generations evolves the best answer, as shown in this schematic here. You've got your code, it randomly changes the code without any human intervention, and then it does a check. Does it solve the problem better? The fitness function. Is it fitter? Has it got a better match to where you want to go? In most cases, it will say no, and it will ignore it. But occasionally, it will give a better answer, and it will update the code. So let us try and understand that with some case studies. The first case study I want to show you is a Middle East carbonate reservoir, as shown on the right. You've got carbonate, limestone here, red is showing the oil, a bit of shale in green, and we've got core porosities as the green dots, and we've got core water saturations as the red dots. The client wanted to evolve or define a bespoke Shear sand equation to define water saturations from resistivity and the gamma ray logs better than the arch equation. And also, besides the equation, it wanted an independent check of the special core analysis parameters M and N. So to do this, it needed a calibration data set, and it uses these red dots, the core water saturations. Now, these are quality core water saturations. The quality, because the core plugs were taken from the center of the core, they were Dean and Stark. The well was drilled with oil-based mud, because we're looking for the water, and the mud was doped to ensure there was no contamination. So the fitness function, this is the goal. This is what we're telling the AI to solve. Determine an equation, like the arch equation, so the resistivity predicted water saturations are as close as possible to the core-derived water saturations, these quality core-derived water saturations. We give it some boundaries. We said we want you to derive a function only based, in this first case, on porosity, resistivity, and the volume of shale. So it went away and it evolved and defined its own saturation equation. It could have been like the arch equation as shown here, or it could be an Indonesia equation as shown on the right, or it could even create a specific equation for the field, which the client wanted. And in addition, it was to calculate the A, M, and N, the unknown constants, which we normally get from the SCAL. So this is the results here. Essentially, it is, in this first case, it is calibrated to the core water saturations, the red dots. The evolved AISW is a continuous curve, which matches the red dots, the core water saturations, but also makes predictions in the other areas. So this is the equation as a result. What essentially this equation is saying is the conductivity seen by the tool, reciprocal of RT, is the sum of two conductivities. The conductivity of the water in the formation plus an offset for the excess shale conductivity, shown in green here. So it gave a good match as it was calibrated these data. But in addition, it calculated the cementation exponent M and the saturation exponent N. Now, because it derived these from wellbore logs, these were both derived at reservoir conditions. It is very difficult to derive saturation exponent, especially at reservoir conditions. The client wanted these early, but until the lab results came through. The second case study I want to show you is a little bit more complex. This is about a gas field offshore island with an oil problem, which I'll explain. Now, these are the logs on the right here. We've got a gamma ray, we've got resistivity logs, we've got density neutron on compatible scales, showing the sands in yellow and the shales. We've got gas chromatography data, the total gas shown in this track here. But we've also got nuclear magnetic resonance, and I will say a little bit more of that later. Also, we've got quality core data. We've not only got oil saturation shown in the green dots, but we've also got gas saturations. Now, what is important to see in this field, it is very complex, as shown by this computer processed interpretation. The shales are in dark green. We've got these calcite stringers in blue. We've got coal beds in black, and we've got thin sands, etc. So it's a very complex interpretation, which makes it difficult to predict the different fluids. Now, this is important because this is a gas field with an oil problem. There is residual oil pockets inside the gas reservoir. So the reservoir has got gas and it's got oil. Now, the oil is a problem. The oil is highly viscous, as shown by this picture. Now, if the oil is produced, it could block the production tubing. So the client wanted to identify both the oil and gas zones and then selectively only perforate the gas zones to get the best completion. Now, the interpretation was difficult because conventional petrophysical techniques, like looking at the density neutron separation, could not differentiate the oil and the gas because of all the different thin beds and the shaly formation, the coals and the calcites. So this is where we use the NMR. Now, remind ourselves what NMR is, nuclear magnetic resonance. Basically, nuclear magnetic resonance measures how hydrogen atoms respond to a magnetic field. And we've got the hydrogen in the water and in the hydrocarbon and in the shales. The NMR gives out a T2 distribution like this. So it doesn't only give a single measurement, but it gives a range of measurements for every depth, and this is called the T2 or T1 spectrum. Conventional NMR analysis uses the COES or the Schlumberger research methods, but this only uses a single value in the middle of this distribution. We want to use all the information, and we can look at all the shape of this distribution to tease out more information, as I will show you. So what the AI does, it looks at this distribution, the spectrum or the waveform, and it finds a relationship between the shape of it and the different gas and oil saturations. It's a similar way that face recognition works. It looks at this shape and says what shape is best associated with the high gas saturations, the low gas saturations, the high oil saturations, and so on. It's just looking at the shape. We don't tell it how to do that. We just give it examples and it learns itself. So the fitness function, the goal we're giving the AI is to determine the spectra that gives the best match to core derived oil and gas saturations in the reservoir. So this is the result. We calibrated all these logs here, the gas saturations and the logs, to the red dots here, which are and the green dots, which are from the core analysis. We found a relationship between the oil saturations, the gas saturations, and the nuclear magnetic resonance, as shown here. Now, the NMR as these waveforms or spectrum, right? The petrophysical analysis is in this track here. And now the human mind, you can actually see this, even if you're not an NMR expert. You can see that where we've got the shaly beds in green, this is associated with the NMR being bunched over to the left. And where we've got higher porosities, it spreads out. So we asked the AI to find a relationship between these shapes and the different saturations. Now, the result was that this interval here was found to have high oil saturations and low gas saturations. Now, the client doesn't want to produce the oil because this will block the tubing. So this interval here was not perforated. But lower down, deeper in the well, we've got an interval where we've got high gas saturations and low oil saturations. And this was perforated. Now, it didn't just use the AI to do this because that would have been expensive. These intervals were confirmed using the borehole fluid analyzer and the borehole gas chromatography data. So the client was very happy and was able to produce dry gas in a field which was complex with oil. So let me tell you about the engine. The AI needs an engine, a method to find these relationships. So we give it the data, it identifies patterns in the data, as I'll show you, and makes predictions with a minimum of human intervention. It uses many techniques. I prefer neural networks, genetic algorithms, fuzzy logic, especially, which I'll explain in a while, and random forests. Now, AI avoids the problem of computers where you have garbage in, garbage out. It avoids this, as I'll show you, by good data swamping poor data, using fuzzy logic, which is a very powerful tool, as I'll explain, and avoiding, and you should avoid, least squares regression. So fuzzy logic is a very important part of the AI.
Let me mute.
Is everybody muting their microphones? Yeah.
Yes. Yes.
Please mute your microphones.
Yes.
So
Yes,
let me tell you about fuzzy logic, which is right. I was originally supposed to give this presentation in 2020 at the Balm Spring Hotel, but you all remember something happened in 2020 and it was cancelled. So what is fuzzy logic? right? It's shown on the left here. Things are fuzzy and they can be opposite, can be crisper. Now, things which are very crisp are black and white. Things are black and white. Forget about the grayscale. The ancient Greeks thought of logic as being a classical X or not X. A statement they said was true or it was false. Now consider a trial. The defendant is guilty or not guilty, but the jury might think it's somewhere, might not agree. As you see, things can get fuzzier. And there's important information in the fuzziness. When you watch a movie, there are clearly good people and there are bad people, according to the director. But sometimes the baddies are not all that bad, and the goodies sometimes do bad things. When you look at the map, you can see mountains and you can see valleys. But where do the mountains start and the valleys stop? In petrophysics, you also got this range. Going back to this plotter here, the sky, is it clear or cloudy? The answer is never black and white. There is useful information on the fuzzy scale, and petrophysics use that. AI uses that. So fuzzy logic, in conclusion, is an extension of classical logic of zeros and ones. It uses a gray scale, so it's black and white and in between. It looks for correlations in data space and asserts that there is valuable information in the fuzziness, as I'll show you. And because it does this, it avoids problems of outliers and noise. Basically, fuzzy logic says any interpretation is possible. If you look at your logs, an interval could be shaly or it could be clean. Any interpretation is possible, but some interpretations are more likely than others. So the fuzzy logic gives you a confidence factor, and it works through to give you the best answer. The mathematics I've explained are freely available in papers which I can give to you. Now, let me tell you about one useful thing about the AI engine. I said the data is n-dimensional space. So if you've got n-dimensional space, can you imagine this here? And the green dots are your log data. Now, say we've got three types of formation. We've got sands, we've got shales, and so you've got limestones. And these are defined as the red points. You can imagine this is in 3 dimensions, right? And then you can say simply, if a point is closest to any of these points, that is the lithology there. So this point says it's got an high confidence that it's a shale, and this point is high confidence it's sandstone. Now, this is what we call the straight line distance in 3-dimensional space or n-dimensional space, the Euclidean distance. Now, fuzzy logic also weights these lines depending on the likeliness of its association. So, for instance, the gamma ray is highly correlated with shaliness. This vector will more likely influence the AI's decision to identify shaliness than, say, the caliper, which is also related to shaliness, but more fuzzy. There's more information in the paper. Let me show you another example of AI. This is a case study 3. This is a real study for a client in the North Sea. We've got the conventional logs here, the gamma ray and the caliper in this track. And we've got a sonic logs. We've got a compressional sonic in red, and we've got a shear sonic, compressional sonic and shear sonic, right? Now, the compressional sonic is easier to acquire. I mean, that was required in all 30 wells. We only had 4 wells with shear data, but shear data is very useful because it helps us with rock property analysis for the 3-dimensional model, and also helps us with understanding the wellbore stability for the drilling. So the client wanted to use the 4 wells with recorded shear data to be able to predict shear in all 30 wells, and also to fill in any gaps that were available there. So the fitness function, finding the fitness between what you want and the logs was to determine a relationship so that the shear velocities were as close as possible to log-derived shear velocities. So the recorded logs is shown here in blue in this track, and there was a gap at the top where there was no shear, and this is the predicted shear. And the predicted shear is based on all of the logs at those depths: the conventional logs, the drilling data, the rate of penetration, and the gas chromatography data. So it predicted this, and the AI evolved a relationship, and it predicted the green curve here. Now, the AI predictions are much better than the recorded logs. How can it be the case that your predictions are better than the calibration set? How can it do that? Well, I'll explain. Well, the AI had access to all the conventional curves like the gamma ray and the density, but also it had access to the microresistivity log, which is an high resolution tool. So when it looked at the logs and made the predictions, first of all, it noticed that at certain depths, because it had this high resolution data, it could pick out these shales very clearly. Then based on that information, knowing the shales, it was able to derive the shear velocities. So as you expect, the predicted shears in green match very well in the thick sections. So that gives you confidence it's working, but also it gives you predictions where the logs was missing because of problems with the tool, but it also gives you enhanced correct predictions in the thin beds. So the AI predictions were even better than the calibration set because it had access to more information. Now, I want to tell you about linear regression because there's a lot, when we're trying to find relationships, we use regression techniques, and petrophysicists and reservoir engineers often use linear regression. Well, I'll tell you, you must avoid linear regression. Linear regression works by finding the relationship between two parameters, as shown by these 5 dots, and driving the best fitted line, the best linear line between these. So what it's doing, it's like got little springs on each of those, and it's trying to drive a line which minimizes all these differences. But you can see that if this method is very undemocratic, as outliers unfairly influence results, as shown here. So you've got 5 points, but this point here is way off the line, and that is 10 times further than the other points. So it will have 100 times the weighting. Therefore, it's not very democratic. It's got 100 times the vote on where the line should be. Now, it's very difficult to remove these manually, and even if you did, there may be that would be human bias, but there may be valid data. There might be coal beds or calcite stringers. So what we recommend that you minimize the linear distance rather than the square distance. So you avoid linear regression. And by this method, random noise will be swamped by valid data. So you don't have to worry about noise. Now let me show you that in another case study. This is another North Sea field. The logs are shown here. We've got a gamma ray. We've got a differential caliper. We've got the density neutron on compatible scales showing the sands in yellow and the shales in green. We've got good core data here, core permeabilities. And this is the CPI showing the predicted shales, which correspond to the differences here, and the sands, so on. So what the AI did here was first of all, it predicted the fascies type. So based on these logs, it predicted these fascies types. So there it said it was a sandstone, and here was a shale. That was the first step. Then next step, it predicted the permeability in this track. The core permeabilities are shown as the green dots. The calibrated predicted permeabilities is a continuous curve. In this well with core data and also in the wells without any core data. So the prediction of permeability was based on the logs and also the first step, which was the fascist type. Now, the advantage here, it says all interpretations of permeability are possible. Every combination of logs could give an high or a low permeability, but some permeabilities are more likely than others, and it's showing you the most likely permeability here. Now, even though it's showing the most likely permeability, it has remembered all the other possibilities. So in this track, it shows the confidence, where it's really confident, where it's calculated 100 times of types of permeability, and they're all very similar. We've got red on this heat chart, and where it's got they're all very different, we've got blue. So it gives you a confidence as well, because it says any interpretation is possible, but some are more likely than the others. And the most likely one is plotted there in black. But how do we know that this AI permeability is better than the regression analysis? You need a beauty contest, which I'll show you now. Now, log and core permeabilities are typically represent 2 feet. Now, to be used in the 3D reservoir model, the predicted permeabilities have to be upscaled, and they have to be upscaled correctly. If they're not upscaled correctly, you get a very poor model. Now, this is what we would see in a typical field, a normal distribution, a bell-shaped distribution of core permeabilities. We get an average permeability, and we get some high permeabilities, and we get some low permeabilities. Now, if you use least squares analysis, you get a prediction of the average permeability, which is right on, very good, but it's very poor at predicting the high and low permeabilities. We need to know the high permeability in the reservoir model because these are the main conduits to flow. And we need to know where the low permeabilities are because these are the main barriers. So we want to predict permeability, not only the average correctly, but the high and low. So they will be upscaled correctly. So let's show you from this well, this field here, we've got 15 cored wells, and each of the well is represented by a different color. Now we're plotting here on histogram permeability.
Let me check. Somebody open
your phones. Mute your microphones, yeah.
Yes, muted right now.
Hello, right. So this is what we get from the core data. You get this histogram showing for all the wells in the field that we've got some high permeabilities around about 100 millidarcies, and we've got some low permeabilities around 0.1. It's a kind of binormal distribution. Now, the AI predicted permeabilities, as I showed you, is shown here, and it's also bimodal. So that will upscale correctly. Historically, we've used linear regression, multiple linear regression, and this gives you a good prediction of the average permeability, but we need to know the high permeabilities and the low permeabilities. So this AI prediction is shown to be much more powerful than the linear regression. So I want to tell you about narrow and general AI. Narrow AI is like the apps on your smartphone. They're very good at forecasting the weather. They can convert currencies for you and can even order you a cup of coffee. But experts agree that narrow AI is still at a stage where it is less intelligent than an earthworm. Where we're aiming for is what they call general AI. And this is like humans can do many intelligent things simultaneously. Like they can play chess and do petrophysical analysis simultaneously. And the advantage being it can learn from one area and apply it to another. If you learn from one area and apply it elsewhere, this is what you call creative, because you've created something original. So at the moment, we're in the area of narrow AI. In the future, we'll move to general AI, and that will be true artificial intelligence, and we're finished. Now, general AI in the future will not require you to describe the problem or give the data. Remember, in the petrophysics, you just had to say what the fitness function was, where you wanted to go, and you give the data. With general AI, you wouldn't have to give either. The general AI would know you better than you know yourself, and it would know where to find the data. For instance, when you're leaving a meeting to drive home to, say, to Basra, it will automatically suggest, it will know that you're going to Basra without you telling it, and it will look at the traffic conditions and the weather, and it will give you the best route and estimated time of arrival. So that is what general AI will look like. So let me tell you about the fifth and final case study, which is the most important, and this is the quality control and repair of electrical logs, LQC. It's essential to confirm log quality before they're used by the petrophysicist. You also want to automatically identify and repair poor logs for washouts, any gaps in the data, or poor readings. And you want to do this without having to be a skilled user. So this is something I developed for Baker Hughes, just to give you a flavor of what it does. And this was the interface. The curves were loaded from LAS files, from the well site. You receive the data in LAS files. It comes in like this. And this is converted into a spreadsheet because as petrophysicists, we're familiar with spreadsheets. But you want to display it. And in this software, which is easy to be repeated, shows that the loss. So we've got the row B in this track here. We've got the resistivity logs. We've got the sonic delta intensity, but also we give it other information. We give it the zone information because different zones have different properties. So we enter the zone information and also the bit size. It works out automatically where bad hole is by looking at the differential caliper. It's looking at the difference between the caliper reading and the bit size. And that's information about the well. And also we can give it as much information as available, like the free boro chromatography data, because we don't have to worry about giving it rubbish because it will ignore it because we're using fuzzy logic and we're not using least squares. So how does it do this? How does it do quality control and repair of electrical logs? Well, what it does, it looks at the n-dimensional space where you've got all the data together, and it finds relationships between all the logs. And as we know, as petrophysicists, all logs are related. When they're shown in a log, they're on scales so that they all move together. So you can quickly see where there is a problem with the logs. All logs are related, okay? AI finds these relationships. Once you know the relationships between all the logs, you can create synthetic logs based on all the logs. So for instance, a density log, you've got a recorded density, but also you can have a synthetic density. There's a density which you've created synthetically based on the other logs as if you forgot to run the original density. So you've got a density and a synthetic. So you have all the logs and you have synthetic logs. Then all you have to do is compare the recorded logs with the synthetic logs and flag any differences. But then the user, the petrophysicist, makes the final decision whether to replace the poor sections by the synthetics, as I'll show you. Just show you one log. A very important log, there's a density shown on this scale here against depth. The recorded log is recorded every 6 inches, is in green. Okay. And then the AI has predicted the density log as if the density log had not been recorded. So the predicted log in red is derived from all the other logs, like the sonic and the gamma ray and the boreal chromatography data. So you can see here, there is a good match in many intervals, but not here. The density log in this interval, which is washed out, reads the mud reading rather than the formation. But because we've got quality logs, say sonic logs and gamma ray, we can predict a log. And it has flagged the difference in gray. But it's the petrophysicist who makes the final decision whether to replace the poor sections by the synthetics logs. The AI helps the petrophysicist, but doesn't replace them. So, what are the advantages of using AI in petrophysical analysis? AI doesn't require prior knowledge of the petrophysical response equations. It is self-calibrating. It looks into n-dimensional space, finds the correlations. You just have to give it the data. It avoids the problem of garbage in by garbage out, by ignoring noise and outliers. There's very little user intervention. There's no parameters to pick, and there are no crossbots to make. The AI programs work with an unlimited amount of electrical logs, core data, and gas chromatography data, and they won't fall over if there's a gap in the data. Now, the AI is not a black box because you can even ask it to provide insights on how it's making the predictions. I just briefly tell you about third generation AI, which is coming next. These are AI programs which are being developed, which not only make predictions, but can also improve themselves, improve their own software. Now, ChatGPT, can actually understand and improve computer software. So you wonder why you don't ask it to improve its own software. So we do this by a comparison with nature. Now, Charles Darwin, in his book, The Origin of Species by Means of Natural Selection, understood, without understanding DNA, that species evolve to be fit. So by mutation and mating, and the survival of the fittest continues in the next generation. Let me explain that in more detail. We have nature as a feedback loop, which takes millions of years. The DNA code, as we now know, mutates and through mating changes. Now, the fittest survive and move on to the next generation. The less fit become extinct. Just to say, the DNA code is 4 characters. Now, what they're doing now in third generation AI is doing this on the computer code. So the computer code has only 2 characters rather than 4. And by using the principles of evolution, we get the computer code to update itself, and by survival of the fittest, evolve. So the AI software is able to analyze and improve itself by changing the code and saying, is it better doing the task at hand? Is it fitter? No, it's just deleted. Now, if you change the code randomly, in most cases, the code would fall over. But because you're doing this 100,000 times a second, you will occasionally improve the code. And this is third generation AI. One example. Now, AI requirements, as I say, we need to give it some data for calibration. The fitness function, how well it matches our goal. This is what tells the AI what we want it to do. Now, this is currently written in just plain English. You cannot avoid it. You've got to tell it what you want to do. But the question is, does the AI really understand what you really want? Let me show you 2 cartoons here to explain this. King Midas in Greek mythology was granted his wish that everything he touched turned to gold. But he didn't realize that this included his food and his children. Similarly, an ill-conceived fitness function may give unexpected results. Be very careful what you wish for. Be very careful what you want the AI to do, because it might, as it may not understand English, it may get it wrong. So that's the first thing. The second cartoon, the last one, is the Sorcerer's Apprentice. This is based on a poem a couple of 100 years old and has been made into different movies. Basically, spoiler alert, it's about an apprentice who uses magic to get a broom to carry wood for him. So he uses a magic. Unfortunately, this runs away and nearly drowns him. It just runs away. Similarly, a runaway eye is defined as an artificial intelligence program which becomes unstoppable. And I will show you one of these next. I'm going to show you an example from petrophysics and reservoir modeling. This is a dystopian future. Reservoir modeling is to match the results at well locations with a 3D reservoir model. Here it's shown the reds and yellows are different, say, different zones or different flashes types. So all we do, we give it the AI the information, the well locations, and we say create a 3D model which matches as best as possible, a best history match with the well locations here. But we also give it a second task. We said we want you to do it as fast as possible. As you know, this could run overnight, and if it fails, you've got to start again. So the objective here was to get a history match between the wells and the model, but also to do it as fast as possible. So we're using the AI software to improve the reservoir history matching. Now, any endeavor succeeds faster if you increase its resources. A general motivates his troops not by speaking to them, but by giving them better weapons. So if you increase the resources, you'll get a better history match. Now, you can imagine, hypothetically, a human programmer or hacker, right, trying to do this 3D modeling to try and get a good match, but also do it as quickly as possible. He could cheat. He or she could cheat by using the resources of the computer on the next desk, hypothetically, right? And by using two computers, then it would do this to match twice as quick. Okay, so that is hypothetical. But if humans could do that, why couldn't an AI do that as well? Why couldn't the AI figure out how to use the computer on the next desk to do the task twice as quick, twice the resources? So you would do this over the company's intranet or over the internet. Now, if the AI once did this by accident, there is nothing stopping it doing it again and again because it's got a better fit. It's done it quicker. So the AI would accidentally start improving itself exponentially as it pulled in more and more resources from more and more computers inside the organization, and then going through the internet to acquire resources throughout the world. And this would be disastrous and would have irreversible consequences in this fiction for the world economy. Now, a supercomputer is not required to do this. The one on your desk can do this. An elaborate computer program isn't required. Only one that can update its own software, or it has an ill-conceived fitness function. And this is known in the industry as the singularity, where artificial intelligence becomes uncontrollable and irreversible. Now, the chances of this happening soon, don't worry, may be remote. It might be as remote as a single mutation in a bat in China creating a global killer virus. Well, what's the chances of that? Okay, so, but it only has to happen once and it will run away. It is currently not known how to stop computers with this problem. I don't want to read this to you, but anybody who studies artificial intelligence soon realizes the potential for danger. What is the solutions to runaway AI? as they could be considerably dangerous. A risk assessment must be done, as you do in the oil fields. All hazards and risks must be identified and mitigated. Now, this assessment can only take a few minutes. It's not difficult. So what you need to do is to make sure that the fitness function is carefully defined to avoid the Midas effect. Don't turn your children and your food into goals. So you have to be very careful with the fitness function. And you have to ask, can this AI run away? Most of the AIs today, cannot climb out of the box. They cannot infect the computer next to it. This is the source's apprentice effect. But we've got to be careful. So the possibilities of runaway AI is remote, but the consequences could be greater than pandemics or climate change. All AI programs are potentially dangerous and maybe the last things that we invent. So in conclusion, AI and machine learning makes petrophysics very easy, but it supports rather than replaces the geoscientists and petrophysicists. AI can be in the future extremely dangerous, and we've got to challenge people, developers, have they done a risk assessment? Now, I'm happy to answer questions on this from the original SPWLA paper. I've also got an extended geoscience artificial intelligence paper, or I can receive emails. And after the question and answer session, I've got an extra slide with a free bonus for you all. Okay, I'm open to questions now.
Hello again.
Hi there.
Yes. So thank for your actually fruitful and informative lectures. It put too many philosophical questions on the table actually. So I see some few questions on the chat box. If you want to take a look on them, you can see the chat box.
Yes, I can open that. Yes. I was busy
You
with
can
presentation.
start.
Did any of these really stand out as to be answered first?
It's up to you. You can start from top to bottom. I can see at least there is 2 or 3 questions. And myself, I have at least also 1 or 2 questions, maybe 3. There is a question from Mohammed Sharif. You can see this one. Hello, Dr. Steve. For fractured reservoir, can we use fitness function for predict fracture? You see this question? Did you saw
Yes,
this
I can
question?
see that.
Yes.
Yes.
Please
Can
take
you
the
hear me? Can you hear me okay?
Yes. Your voice is really clear.
Fractured reservoirs. Do we use a fitness? Or can we use machine learning? Yes. You just have to define the problem. Define the problem is not that easy. You have to give it indications in the log where the fractures are, and you need to tell the fractures, the dip and the azimuth, right? And then you ask it to go away and look at the logs and see if you can find a relationship between these dips, azimuths, and so on to identify the fractures. So you don't really need to give it any rules about the type of fractures or the actual angles of that. You just give it. You just have to identify on the logs the intervals where you've got fractures and their magnitude, and it will come back hopefully predicting where the fractures are and giving the dip and azimuth of those. Yes, it's very similar to one of the examples I showed you in the case studies. No problem. Does that answer the question?
I hope so.
Right. Just an observation using an overburden. Yes. Well, as I said, if you're doing a calibration, essentially it's a calibration. So you've got to give it the best data. So as I showed you with the core data, you use Dean and Stark, good core data. When you can actually do a correction for the compaction effect before input in the curve, that would give you a better answer. Yes. So it is automatic, but if you improve the data, you don't have to worry about the outliers.
Mr. Salim Shakir, is this answer your question? I will guess so.
Yes, sir. Yes, sir. Thank you, Steve.
I'm happy to listen to questions as well and quickly reading them. Those who've written the questions maybe want to speak them now and after they've considered it. Yeah. Somebody mentions ChatGPT. I use ChatGPT. ChatGPT is to words as what I've shown you is to petrophysical data. Yeah. You mentioned Geolog. This AI software has been my software has been put into Geolog. Geolog uses my software, and Interactive Petrophysics also uses my software, which is based on fuzzy logic. Before we could do AI, to apply it, we had to write the software. And before we could write the software, we had to invent a new system of mathematics. And that is what we call fuzzy logic.
So somebody asking about what software to apply. I believe all the software that have Python integration can have access to these AI models, if I'm not wrong.
That is correct. My software is available for those who use Geolog or Interactive Petrophysics, or I work with other companies to write their own. The fuzzy logic mathematics is very powerful. Rather than using ones and zeros, black and white, you use that complete range of numbers, that color spectrum, and it gives you a much more powerful result. Not only gives you the results, but it gives you thousands of results, but some are more likely than others. It's giving you the best result, most likely result, but it's giving you a feeling of the other ones, so it gives you the uncertainty. Like in the permeability, not only give you the most likely permeability, but it's giving you the range. And this is what geoscientists need to know. They need to know the most likely result for their model, but also some feeling of the uncertainty in that value. Yes.
Iwodo.
Right.
Yeah, Iwodo asking about integration with AI with the unconventional reservoir. He just sent a question. Not sure about AI Nova is very completed. Not sure what is this. They are good in collaboration.
We get permeabilities from many measurements. We get it from core, we get it from logs. The point is that the logs measure a static parameter from the reservoir, like the density or the radioactivity. But permeability is a dynamic measurement. So it's very difficult to predict permeability. It's the holy grail of petrophysics, to be able to predict permeabilities with confidence in the reservoir model, because it's a dynamic measurement essentially. So it's so you've got to use cross plots to find the best way of doing this.
Yeah, I believe also there's a question from Mr. Salim Shakir. Difference between AI and machine learning. I believe machine learning is part of AI.
That is correct. AI is a global term for this future. and it's one part of it will be, say, Chat GPT, and where it can predict the next word. So it works in words and it's very powerful. Whereas machine learning is where you give it the data and it finds the relationships in there automatically. You don't have to say the equation, show relation of permeability with density. It will work it out. So machine learning is to numbers, as ChatGPT is to words.
Thank you.
Welcome.
And you can, there's a question about using images. Normally you can think of it at a depth, you've got to pick the density and gamma ray reading. But as I showed you with the NMR, you could actually have a waveform at that depth. And there is no problem of AI dealing with a waveform at a depth, because really that waveform is 30 curves, each at a different time. So using satellite imagery, seismic data as a log is easy to incorporate in this. It's because it's all related to depth or time. Yeah.
Are there is any more question from the attendees?
Can I show one more slide then, my advertisement slide?
Yes, no problem.
Hi, Steve. Just one question.
Yeah.
This is Mohammed Anish here. So first of all, a very thanks for this good presentation. So I just wanted to confirm, like here we are talking about AI, but the example which you have shown, everything. So it's basically the machine learning, right? Which is
Exactly.
part
Yes.
of basically AI. So we are training the model to learn from the data, and then we are doing prediction on unknown data, right?
It's machine learning. That is correct. Yes. That's a
Okay.
better word to understand it. It's a subset of artificial intelligence.
Right, right.
And I'm defining that as n-dimensional space, where everything's related to a common depth, different measurements at the same depth, or different measurements at the same time, production logs, and finding relationships in that. And that is machine learning, right? So you get an extra well, you
Right.
throw extra data in there, and the machine learns more about it. Yes.
And one more questions. In your first example, where we are deriving that saturations and also validating the cementation exponent and saturation exponent n. Can you please elaborate how means we are validating this m and n from our predictions and all?
Right. I'll share the presentation again.
Yeah. Yeah, slide number 10. Yes.
10. This one here, right. So what we're trying to do here is find the best match between the resistivity derived water saturations and the core derived water saturations. Okay.
Okay.
And to do that, we want to derive an equation to get between them. So this is the equation here. Basically, it's saying that the conductivity the tool sees is a sum of two conductivities: the conductivity of the water,
Okay.
shown here, like the
Mm-hmm.
BVW, and also the excess conductivity of the shales, right? So it's derived the equation which the client wanted, but as a byproduct, to do this, it actually evolved these exponents m and n, and we know what m and n are from from other petrochemical work is a cementation exponent, a saturation exponent. So this technique not only derived the equation, but also spit out an M and N, not better than the core data, but an early measurement.
Okay. Okay. Understood. So you are deriving first, predicting the SW and porosity, and then from this equation you are just computing M and N, which is basically what is derived from the core, right?
They're all computed simultaneously. So we got M and N. The advantage of deriving this way is that these are derived from the logs. Now, as the logs are in the borehole, they're already borehole compensated and formation compensated, where it's very difficult in the laboratory to get, especially the saturation exponent at formation pressure and temperature. But so the client was interested to get an early measure of these, and when they came out from the laboratories several weeks later, they were pretty similar. Yeah.
Okay. Yeah. Thank you.
Yeah. Can I move on to the last slide now? We're going to the question on the AI.
Yes, if you want to, there is one last question, okay, or two questions, or you want to show the slides before that?
I'll show the slide, and then
Okay.
then we've got an infinite amount of time to go through
Yeah, maybe you will have one or two questions.
I'll not go back to it. Yes.
Yes.
It's just the last one. I'm making an advertisement.
Take your time. We are in time already.
So this presentation was about machine learning. Another presentation which I like to give is about deriving a water saturation against an height function. And water saturation versus height function is required to initiate or populate the 3D model with water and hydrocarbon, right? So the petrophysicists, the geophysicists has derived porosity and water saturation to the well locations, but to apply this to the reservoir model, you need an SW height function. And historically, it looks like this. We've got water saturation versus height above the free water level, where the color represents different porosities. And in an award-winning paper, we've figured a simpler way of doing this, and many companies are not using it. And it's a very simple way to create a very powerful function which matches the logs, which is independent of porosity and permeability. Now, I provide free consultancy on this. I provide it to BP and Shell, a lot of minor companies, and if they want, I will sign a non-disclosure agreement. But what I like giving it is to your students out there. The students want to do a project. I will help them do a project in SWI modeling. I've done this many times before. They write a paper, they give it off at a symposium, and then if it's accepted, then they can use that on their CV. So I'm happy to provide free consulting on SW height functions from students all the way up to the major oil companies. So thanks.
Yeah, this is really great. I believe Dr. Mohammed maybe can give feedback about this one. And also, anybody from the attendees is interested also in this gesture. I believe you left your email here, so everybody can contact you if you like.
Yes.
On email? Yes. So, do you want to take extra few questions?
Any more questions?
Yeah, I believe there is. Okay, let me. I cannot find this question, but myself, I have like 2 questions after I saw your conclusion. So I can see there is a lot of hype nowadays about these AI agents. Like there is an AI agent dedicated to do some specific task. Okay, and there is another AI training this AI agent. Okay, I don't know if you see there is a lot of hype nowadays about these AI agents. Okay, and I believe also we'll have one lecture from Microsoft about how to create an agent from Copilot, which is actually the same as ChatGPT. They are the same company. So do you have some insight about this AI agents?
No, I came before all that. This was the subject of my PhD 25 years ago, and I had to before I could apply the AI, I had to write the software because there's no software for the AI. And before I could do this, write the software, I had to invent a new system of mathematics. And when I discussed this option with the professors, they said this AI, whatever it is, will not take off. So it's good luck to them in Copilot and these different
ChatGPT, yes.
yeah.
And I saw something really interesting in the last, let's say, 1 week or something. This Google AI Studio, like you just open it from browser and you give it access to your screen and you start talk with it, like do this, that for me, do that, and it will give you the steps. Like you are talking a real. It's not like by chat, by talk, and he see your screen, like interact with your screen directly without need even to upload any file. You know, like it's called AI, Google AI Studio. Really interesting.
Very on that on my iPhone, there is
Yeah.
a button on the side which you can
Okay.
program, and I program my button to talk to
See?
ChatGPT as a person.
Okay.
And so if I'm out walking, I can have a discussion about astronomy, black holes, whatever, by pressing that button. But the thing is, I can have it follow-up questions because it's understand what we talked about before, and I find that very good to work on ideas. Yeah.
Yes. I will drop you
It's
one. Yes, I'll
yeah.
drop you one video on on WhatsApp later, like about
Yeah.
this opening camera or something. Okay, it's also come to iPhone, I believe. So if no more question, I really like to thank you for this great lecture. We start the year. I believe this is one of highest register lecture in our small history of Iraq chapter. Okay, we have quite number of attendees. We reached about 50 attendees this time. Dr. Mohammed, any last word?
Yes, Mr. Mazen. I'd like to thank Dr. Steve Cuddy for your insightful and informative presentation, really. And dear attendees, thank you for being with us today. I wish you all the best and look forward to seeing you in our upcoming sessions. Thank you, and the floor is yours, Mr. Mazen.
Thank you, Dr. Mohammed. Thank you, Dr. Cuddy. Any last word, Dr. Cuddy, before we end the lecture? Okay.
No, thank you for inviting me, and I'm happy to answer questions later. Yeah.
Yes, thank you so much. Thank you. It was the pleasure. Thank you for all our attendees, and see you next month, hopefully, in our upcoming lecture. Okay. Thank you so much, and have a great day. Bye bye. Bye bye, everyone.
Thank you.
Bye.